Okay, hello everyone. Welcome back. Hope you all had a good weekend. We are going to continue with chapter 15. So there will be an Achieve posted for the content that we covered this week, but it won't be due until after spring break. So you have some extra time. And then I don't think we'll finish chapter 15 this week. We'll finish it when we come back. So let's just get right into it. At the end of class on Friday, we briefly talked about equilibrium and what equilibrium is. And so we looked at this equation and we filled all that in, where this is a gaseous reaction at equilibrium. So if you have a container, you put hydrogen and nitrogen gas into it, those two molecules will react with each other to form ammonium, the NH3. But also, if you had a different container and added ammonium to it, ammonium would decompose and form hydrogen and nitrogen. Ammonium forms hydrogen and nitrogen forms ammonium. So what really happens in either container is that as nitrogen or hydrogen is reacting to form ammonium, ammonium is decomposing to form nitrogen and nitrogen. Both are happening at the same time. So in any container, you have a mixture of both hydrogen and nitrogen, the reactant side on this slide, and ammonium. They'll always be a mix because they form each other. So this reaction is a reversible reaction. Reactants will form products and products will form reactants. And so we can describe the equilibrium of this reaction as a certain state. So we'll describe what that is on the next slide. Okay, so what we mean by equilibrium is that we have a reversible reaction in the rate at which the products are being formed is equal to the rate at which reactants are being formed. So the rate of the forward reaction is equal to the rate of the reverse reaction. So rates are equal. Rates of reactants forming products equals rates of products forming reactants. Another way to describe this, because the rate of the forward reaction is not changing, because that means that the amount of product present, which we describe as concentration, the concentration of those products is not changing. The concentration of the reactants is not changing. So concentration of reactants and concentration of products remains constant. At equilibrium, a reaction has reached a state where the rate of the products being formed equals the rate of the reactants being formed. That rate remains constant. So overall, the concentration of products remains constant, the concentration of reactants remains constant. But equilibrium is dynamic. So what is not true is if a reaction reaches equilibrium, then it's done reacting. Everything's stable, nothing's happening, we've got a certain amount of products, certain amount of reactants. That's not the case. What's true is that reactants are still forming products and products are still forming reactants. They're doing that at an equal rate, so overall the concentration of reactants and products doesn't change. But they are still reacting. It's just like when we talked about vapor pressure equilibrium, where you have that image of the liquid, and above the liquid there are gaseous molecules, And at any given time, liquid molecules are evaporating to form a gas, and gaseous molecules are condensing to reform into the liquid. That is constantly occurring back and forth, but the net amount of gas present and the net amount of liquid present isn't changing because they're constantly exchanging phases. Same thing is true for a chemical reaction at equilibrium, where the reaction is forming products in the forward direction and is reacting in the reverse reaction, but the amount of reactant and product is not changing overall. We got a graph on this next slide. So this graph here, we have time on the x-axis, rate of reaction on the y. The red line represents the forward reaction. We're describing the forward reaction as starting with ammonium and forming H2 and N2. And then the reverse reaction is these two gases reacting to form NH3. So looking at this graph here, we initially start with a high rate of reaction for the forward reaction because we're starting with NH3. And so if we have a high concentration of NH3 or reactant at the start of the reaction, then the reaction goes quicker. We learned last chapter that as reactant is used up, the reaction rate decreases. So the reaction rate is decreasing over time until it reaches a certain point and then it remains constant. The rate of the reverse reaction, so starting with H2 and N2 and forming NH3, is 0 at the beginning because only NH3 is present. We need some H2 and N2 to be present for that reverse reaction to occur. So the rate slowly increases as H2 and N2 are produced, and then reaches a point where it remains constant. So the question here is to mark when, on this graph, when does that reaction reach equilibrium? What point on the graph represents the start of equilibrium conditions? Mark it, show someone next to you. In a few seconds, I'll ask for someone to explain. Okay, where is equilibrium reached based on this? Yeah. The point where they meet and they become equal to each other. We said that at equilibrium, the rate of the forward reaction equals the rate of the reverse reaction. So as soon as they are equal to each other, that's also the point where the rate stops changing. So right here is where equilibrium is reached. They've reached equilibrium. When we write a chemical reaction that is reversible, if a reaction is reversible, it can exist in equilibrium. We use that single-headed arrow pointing to the product side, single-headed arrow pointing to the reactant side. This implies that both the forward and reverse reaction occur. And at a certain point, this reaction will reach equilibrium. This is different from this, where I have a double-headed arrow and a double-headed arrow. This is convention. You might see that online. I don't know what you're going to find online, but we're using this in our class. This is what you'll see most. This is in your book. This is what you'll see in organic chemistry. So single-headed arrows for equilibrium reaction. So let's talk more about how we're representing, how do we know what's a product and what's a reactant if it's reversible, right? So that equilibrium arrow, which we've talked about, this indicates that the reaction occurs in both directions, forward and backward, at the same time. The forward reaction, now this all depends on how the equilibrium reaction is represented on the page. If we have NH3 on the left side, that means that the forward reaction is NH3 forming H2 and N2. The reverse reaction are the products forming reactants, so H2 and N2. Forming NH3. But either set of substances can be placed on either side, but if you switch the locations of NH3 with H2 and N2, then that switches what we describe as the forward reaction and what we describe as the reverse reaction. So it's all, this is relevant or dependent on how the equilibrium equation is written out. But no matter what, the left side we call the reactants and the right side we call the products. Forward reaction is left to right, reverse reaction is right to left. So let's say we describe left side as reactants and right side is products. Yeah.
Where did the two go? Toward that NH2?
Thank you. Was that the same? I saw another hand. Yeah, same thing. Yeah. Okay, so you can switch the sides of where you have reactant and product, but then that will describe them differently, right? We always have forward reaction left to right. Okay, so now the question is, if we have a reversible reaction, how do we describe the rate? How do we describe what equilibrium looks like? We'll do that in this next section. We're going to talk about the equilibrium constant, and this is used to describe the state of equilibrium. I'm talking about this in my organic chemistry class right now as well. So just keep in mind, you'll see this again. So remember that equilibrium occurs when forward and reverse reaction rates are equal. So for a reversible reaction, we have a new example here. This is atomic iodine forming diiodine. The forward rate constant for a reversible reaction is still K. So we're talking about lowercase k, that rate constant. If you're talking about a reverse reaction, often there is a subscript of 1. Sometimes that's included, sometimes it's not. This is for the forward reaction, so the rate of the forward reaction. The rate of the reverse reaction is K with a -1 subscript. So we're showing that with these two here. So the equilibrium equation is atomic iodine forming diiodine. The forward reaction is atomic iodine forming diiodine that has a rate of K with subscript 1. The reverse reaction is diiodine forming atomic iodine, and the rate is described as K with a subscript -1. So you'll see that used by convention in the book and in your homework questions. So we can describe the rate of each of these individually using what we learned about elementary steps. The rate of the forward reaction is equal to the rate constant, so we're just going to write K with a subscript 1, times the concentration of reactant, atomic iodine, raised to the power of its coefficient. So we learned that on Friday, maybe? It was last week. One day last week. So this is a bimolecular reaction. 2 atoms of iodine are required for this reaction to occur. So So we have concentration of iodine squared. The rate of the reverse reaction, we have a different equation here. K with a subscript -1 to indicate this is the rate constant for the reverse reaction, times concentration of diiodine. So we write the rate law for each reaction individually. We have a different rate constant, different reactant for each of these rate laws. But at equilibrium, they are equal to each other. Rate forward equals rate reverse. So K times the concentration of iodine squared equals K -1 times the concentration of diiodine. So I'm just setting these two equations equal to each other. Just going to draw that line to separate them. So this will be used when we talk about the rate, no, equilibrium constant, sorry, not the rate constant, equilibrium constant, we will use this relationship. We've got two more graphs to look at on the next slide. Okay, looks like we're ready. Two more graphs describing equilibrium. So notice, let's look at the one on the left first. Here we're looking at concentration of reactant and product over time. So we're assuming we're starting with atomic iodine. Looking back at the equilibrium equation is written, again, atomic iodine forming diiodine. So adding atomic iodine will begin reacting, and so the concentration of this decreases until equilibrium is reached. The concentration of diiodine is being formed at the beginning. It continues increasing in concentration until equilibrium. So at equilibrium, the concentration of I is not changing, the concentration of I2 is not changing. So the concentration of each one remains constant, but the concentrations of each other are not equal. Concentration of I does not equal the concentration of I2. It's possible for that to happen, but that most often we'll have different concentrations of reactants and products. So at equilibrium, let's just write concentration of reactants and products remain constant but not necessarily equal to each other. That is a very common mistake that students will think that the reaction reached equilibrium, so reactants of product or concentration of products equals concentration of reactants. That is not true for the most part. There are exceptions, but that is not a statement we can make. What is equal is the rate of the forward and the rate of the reverse reaction, and that's what this is showing. So adding atomic iodine at the initial part of the reaction, the rate is high until iodine is starting to be used up. That rate decreases because the concentration of the reactant decreases until it reaches equilibrium. At that same point, the rate of the reverse reaction is equal to the rate of the forward. So at equilibrium, rates are equal and constant. Questions on these relationships? Yeah.
So I was going to ask you, it's saying that, like, not necessarily equal to each other as in the concentrations or not.
Of products and reactants. Yeah. Okay. So these properties are used to define this equilibrium constant. So this is capital K, different than the rate constant, which is lowercase k. Capital K is generally concentration of products divided by concentration of reactants at equilibrium. So on the left side here, we'll show how we derive the equation for K, and then we'll write that for a generic equation as well. So for the equilibrium reaction we've been talking about, iodine forming diiodine, at equilibrium, the rate of forward reaction times concentration of reactant squared equals rate of reverse reaction times concentration of product. We can rearrange this to get rates on one side and concentrations on the other. So if we divide both sides by K minus 1, so the rate of the reverse reaction, and divide both sides by I squared. So what this will do is we'll cancel out K to the minus 1 on this side. We'll have it in the denominator over here. And then dividing by concentration of iodine squared, we'll cancel it out on the left side, and we'll have it in the denominator on the right side. So we will have now rate of the forward reaction divided by rate of the reverse reaction is equal to concentration of product divided by concentration of reactant. And that ratio is K. So here we have product, reactant. Based on the way that the equilibrium reaction is written on the slide. So I2 is the product, iodine is the reactant. Notice that the coefficient is now an exponent in that K equation. So that will be the case for all other equilibrium reactions. So for a general reaction where we have reactant A with coefficient lowercase a, reactant B with coefficient lowercase b, products C and D, K is the concentration of each product raised to the power of its coefficient divided by concentration of each reactant to the power of its coefficient. All right, let's talk a little bit more about why we care about capital K. For any given reaction, K will always be the same no matter the initial concentration of reactants. K is a ratio of products to reactants. So if you're adding more reactants at the start of the reaction, that will form more products. And when that reaction reaches equilibrium, it will still have the same ratio of products to reactants. So it does not depend on initial concentration. It will be the same for a given reaction. Depends only on the specific chemical reaction. And the temperature. Temperature can influence the value of K. We'll talk more about that later in this chapter. But it does not depend on other factors that affect reaction rate, like particle size or the presence of a catalyst. The equilibrium concentrations will still remain the same. When you're writing out the expression for K, we are only talking about substances in their concentrations. We can describe the concentration of a gas in a container, and we can describe the concentration of something dissolved in a liquid. So it is an aqueous. We'll talk about aqueous solutions. So something in an aqueous state. But we do not describe the concentration of a pure liquid. That's the container, and we're talking about concentration relative to the amount of that pure liquid. And then we also don't describe concentration of a solid if it's not dissolved. So we do not include solids or pure liquids. Only aqueous species and gaseous species have concentrations that can change. So when you're writing out the expression for K, you leave out liquids and you leave out solids, but you include gases, you include aqueous substances. And then sometimes you'll see this as K with a subscript EQ for equilibrium. Okay, with all of that in mind, we got two questions here. Two reactions, and you are writing the K expression, the equilibrium constant expression for these two reactions. If you finish this one early, go to the next slide and try that one out as well.
No, because this is, so it should be age plus grade.
About 30 seconds. Okay, I'm gonna end the iClicker here. All right, first equation, silver sulfide, forming ions, silver plus and sulfur 2 minus. Remember, K is products over reactants. So first product is silver with a +1 charge. That is aqueous, and it has a coefficient of 2, so it is raised to the power of 2. Next we have sulfide, S2 minus, also aqueous, with a coefficient of 1, so raised to the power of 1. And that's everything for the products. Reactants go in the denominator, but here our reactant is a solid. On the previous slide we said equilibrium constant expressions do not include solids or pure liquids. So all that we have for that equilibrium constant expression is silver and sulfur, and that's it. Yeah. When it has a coefficient. Yeah. Okay, next one, we have product H2CO3. This is aqueous, so we include it in the numerator. Then reactants are CO2 and H2O. CO2 is aqueous. So we include that, but H2O is a pure liquid. So we do not include H2O in the equilibrium expression here. So equilibrium expression for reaction B is this one product over that reactant. We got any questions about this? All right. Then let's go to the next question. So this one will also be an iClicker. Let me get it started. What happened? So here we have an equation where the equilibrium constant K is provided. So we know the value of K, and the question is there more A or B at equilibrium? We're talking about a general reaction with reactant A and product B. So given the value of K, which reactant or which material is in higher concentration? So it might be helpful to write out the maybe write that somewhere in the and then think about what that means. I'm not totally. Okay, I got it. Yeah, so think about, well, it might be helpful to write the equilibrium like product over reactant, and then with the value that's provided, what does that tell you about the ratio? Is the denominator larger or the numerator? And it also might be helpful to write that as like that inside the Yeah, so it might be helpful to write out the expression like A equals concentration. So then that ratio B over A is equal to this value. So does that tell you if A is? So I have kind of. It's 10 to the negative 3, so it's, yeah, so. All right, I will end it in like 10 seconds. I think this is everybody, but Justin, oh, that was nowhere near everybody. Okay. All right, now I'll end the iClicker. Let's see what you all were thinking. More for A, but definitely a mix. Okay. So here we have the value of K, and we know what reaction we're talking about. It is generic, but we can still write the equilibrium expression. So that is K is equal to concentration of product, B, over concentration of reactant, A. And we know this value is 1.6 times 10 to the negative 3, which is 0.0016. So the ratio of B to A is a small number. It is a decimal, not a whole number. So that means that B must be smaller than A. So that means there must be a higher concentration of A at equilibrium than there is B. So we can use the value of K to understand which side of an equilibrium reaction is favored. Is the reactant side favored or is the product side favored? In this case, for this generic reaction with a K value of 0.0016, this tells us that at equilibrium, the left side of the reaction where the reactants are, that is favored. There's more reactant than product, and we know that because of the K value. So K is used in general to determine reaction favorability. So for any reaction, sorry, you can't really see that top row very well, but for any reaction where we have reactants forming products, K, concentration of products, divided by concentration of reactants. So we have three possible conditions. We can either have concentration of products equal to the concentration of reactants. That means that the numerator equals the denominator. That means that the fraction is equal to 1. So K is equal to 1. If K is equal to 1, then neither the forward or the reverse reaction is favored. They're equally favored. So right here, concentration of reactants equals concentration of products. So that it can be the case for certain reactions. For other reactions, K at equilibrium can be greater than 1. That means that the numerator is larger than the denominator. That means that there's more products at equilibrium than there are reactants. So concentration of reactants is less than concentration of products. The numerator must be larger than the denominator for K to be greater than 1. So that means there's more products at equilibrium than reactants. That means the forward reaction, going from reactants to products, is favored. We can also say the reaction, I'm abbreviating as RXN right there, the reaction lies to the right. You'll see that expression a lot. Where if K is greater than 1, we have more products. Products are on the right side of the equilibrium equation, so we say the reaction lies to the right. And then the last possibility, which is what we saw on the previous slide, is where K is less than 1. So it is some decimal. That means that there are more reactants than products at equilibrium. That means that the reverse reaction is favored and the reaction lies to the left. So we've got three possible conditions at equilibrium. There are questions on this, yeah.
I don't get what it means to like lie to the right, lie to the right.
So if we have, for K is greater than 1, we have more products than we have reactants, then for any reaction with reactants on the left and products on the right, lying to the right means we've got more products at equilibrium because products are on the right side of the reaction equation. And then if we have more reactants at equilibrium, that's on the left side, so we say reaction lies to the left. All right. Well, we'll be done with notes. I have your midterm Scantrons. So that was funny. So I'll pass these back, but I've got a few things to say first. There were 24 questions. It's out of 60 points, just like every other assessment. So each question is worth 2.5 points. So what you'll see on here is your score, like how many you got correct out of 24. And I will multiply that number by 2.5 when I add it to the Blackboard gradebook. Two more things. The Scantron key that I used had the wrong answer for question 1, but I've already corrected them, so you have the correct score on here. And then I will check before I input all the grades and input your midterm grades. I'll check to see for those of you that did the extra credit, and I'll add it to this score or the first exam, whichever one is lower. I'll post the key later today or tomorrow, and then review it. Let me know what questions you have. It's a good way to study. The final is cumulative, so please don't completely move on from this content. And then, yes, let me know if you have any questions. Clara? Clara? Oh, you're married. Yeah. Yeah, I'm gonna do the library. Yeah. How much? It's 1 point per assignment, so sort of like I will add 1 point to the gradebook score for the exam, so I will add up to 4 to the score. Whatever.
Yeah. Let me stop the recording real quick.